Okay, today in class we did some binomial calculations in R. So we're in the file plot underscore binomial underscore significance dot R. So we ran this first chunk of code, and by the way, to send code from the R document editor on the left side of the screen to the console on the right side, I'm highlighting the code and pressing Control Enter, and that will send it to the right side. So here, as you recall from class, this created a plot of the binomial probabilities, and the values of k colored gray are those correspond to values of p hat, which is k over n, for which we fail to reject a null hypothesis under this decision rule. And the significance level for this test and this decision rule we calculated as 0.29. The next part does the same exact calculation except for d equals 0.12. So in this decision rule, we reject h naught of p equals 0.24 if p hat is more than 0.12 away from 0.24. So this does the same plot. It shows the acceptance region for this decision rule in gray here. And again, we can calculate the significance level for this decision rule, which is 0.0327. So most of the time when you do a statistical test, you take the significance level to be some small number, such as 0.03. So this would be a reasonable significance level for most tests. Okay. Now this is new stuff. So this is a power calculation. So remember, the power is defined as the probability of rejecting the null hypothesis when the null hypothesis is false. So in order to do these calculations, you have to hypothesize an alternative value of the parameter. So the value of the parameter we're hypothesizing as the alternative is p equals 0.16, which is less than the university-wide proportion of students from New York State, which was 0.24. So to do the power calculation, I use the same exact decision rule. So we're going to reject if p hat is more than 0.12 away from the null hypothesized value, which is 0.24. But we're going to do the probability calculations assuming an alternative value of the probability of 0, and that alternative value is 0.16. So here in this line where we compute probabilities in the binomial distribution, the first two arguments are the same. So we're computing binomial probabilities of values of 0 up to n, which is 60 in this case. The size, so the binomial n comma p, is n, but the probability now is p1, which is equal to 0.16 in this alternative universe. Otherwise, the plot is constructed the same way. We're going to color the values gray, for which we fail to reject, and the values black, for which we reject, but the actual probabilities are going to change. And in this case, they'll be shifted towards the left, since p is smaller in this case. So these are all the same commands that we did before. So here you can see in the plot that the center of this binomial probability distribution, it's centered at 0.16 instead of 0.24, which is the null hypothesized value. So to compute the power, all you do is add up these binomial probabilities in black. And most of the probability mass is on the left side. So there are some values in black here, but they don't contribute much to the power. All right, so this is the same calculation. So the power of this test is 0.235, which is probably a little bit too small for most practical purposes. Okay, so up to this point, we've been specifying our decision rules. So I've just been making these numbers up, D equals 0.06 and 0.12. But the way this usually works in practice is that we specify the significance level, alpha, as 0.05 or 0.01, and then we figure out what the decision rule needs to be in order to have a false positive probability or rejection probability equal to alpha. So that's what this chunk of code does. And the way we're going to do this is we're going to pick a bunch of different values of D. So these are the values I'm storing in dvec. So dvec is a big long vector. Length of dvec is 2401. So these are the values of D that we're going to try. So and for each value of D, remember we're rejecting if p hat minus p is bigger than or equal to D. For each value of D, we're going to compute the false positive probability, the rejection probability. And then we're going to pick the value of D that gives the right significance level of 0.01. Okay. So before I was typing in 0 up to n manually in the binomial calculation, so I'm going to give that a name. I'm just calling that kvec. So kvec is just the numbers from 0 up to 60. And then for each value of D, we're going to store the rejection probability in a vector. So I'm going to initialize that vector. So that's what this command does. So there are various ways to initialize vectors. One of the ways is to use rep. So if I do rep of 0, 10, it will repeat the number 0 10 times. If I do 0.99, it'll do this. I'm just filling this vector in with missing values. So that's what reject prob is. So for each value of D, I'm going to fill in the corresponding entry of reject prob. Okay, so this is going to be a for loop, so we can iterate over the entries of dvec. J is my iterator variable, and we're going to iterate j from 1 up to the length of dvec. And then for a specific value of j, we're going to extract dvec of j, so the jth entry of dvec, store that as d. And then here we're going to figure out which values of k correspond to the event that k over n minus p absolute value is bigger than or equal to d. So kvec over n, these are numbers from 0 to 1 because k goes from 0 to 60 and n is equal to 60. Kvec over n minus p, we're just subtracting off 0.04. And then this comparison, absolute value kvec over n minus p is greater than or equal to d, picks out which entries of this vector are bigger than or equal to d. So, for example, your d is 0.999. Let's specify this. So let's say j equals 1,000. Your d is 0.099. These are the values of k such that kvec over n minus p is bigger than or equal to d. So if I do kvec of ins, these are the entries of kvec. These are the values of kvec for which k over n minus p is bigger than or equal to d. Okay. Now, to compute the rejection probability, I just take those specific values of k. I compute the binomial probabilities for n comma p, and then I add them up. So this does d binom kvec n comma p. These are binomial probabilities, and then add those up. This gives the rejection probability for setting d equal to 0.0999. So this is larger than alpha, so we're going to need a d that's larger than 0.099. Okay, so that's the explanation. This is the code. It runs immediately. It did this over 2,400 values of D. And then the rest of the code just is to figure out which of those corresponds to a rejection probability of 0.01. Okay, so this is our significance level. This comparison, so we're not doing an assignment in this line, I'm just showing how this comparison works. So reject prob less than sig level, these are a bunch of true-false values. If I do dvec of those, these are the values of D for which the rejection probability is less than sig level. And what I want here is the smallest such value. So this is the smallest value of D such that the rejection probability is less than significance level. And I'm going to assign that in a variable min D. So remember, we reject if P minus, let's see, P hat minus P is bigger than or equal to min D. So in this case, we're going to fail to reject, with this value of D, we're going to fail to reject if P hat is between 0.0966 and 0.384. But if P hat is outside of this interval, we are going to reject the null hypothesis. The next chunk of code plots those rejection probabilities as a function of D. So here you can see, what are we printing out here? We're printing out the values of D for which reject. Reject prob, these are all the rejection probabilities. And so these are a little bit hard to look at because it's a vector of length 2400. So I want to visualize this for you. So this first line, it sets the margins of the plot. So par is a function to set plotting parameters. Mar is one of the parameters that you can set. So this is mar for margin. And I'm picking some values that made the plot look nice. Set up the plot. Add some axes, so this is the same as before. I'm doing these axes manually. Box puts a box around the plot, which makes it look nice. And then I'm going to add some lines to the plot. So the lines I'm going to add, I'm going to put a magenta line at the significance level, which we set to 0.01. 0.01. And I'm going to add a blue line at the value of D that we selected. Okay, so now the plot's complete. Let's go over to this side and explain what this is. So we're rejecting if absolute value of P hat minus P is bigger than or equal to D. And these are the values of D. So remember, we tried out to start D equals 0.06. And so that would give a rejection probability somewhere up here. Specific value was 0.2 something, as I recall. And then this is just a plot of those rejection probabilities as a function of D. So the value of D we pick is the value that gave a rejection probability, the first one, as we're moving in this direction, that gave a rejection probability of less than 0.01. So that happens to be D equals 0.1434. Okay, so this is just a visualization of that calculation we did in the for loop before. Okay, so the last thing I want to show you on this part is just to verify that we did this properly. So these are the same calculations that we did above for D equals 0.06 and 0.12, but I'm doing it for the value we selected, which is 0.1434, and showing that this number actually is less than 0.01. Okay, so this is just to show you that we did the right thing. Okay, so the last part of this code is to show how to construct a confidence interval using these concepts. So as you recall in class, one way of creating a confidence interval is to do a bunch of hypothesis tests, and then do a bunch of hypothesis tests for hypothesized values of the parameters. And our confidence interval consists of those parameters for which we fail to reject the null hypothesis that that parameter was the true value. And we did a calculation, very simple calculation in class to show that actually is a 1 minus alpha confidence interval. So what I want to do is, for the little survey we did in class, I'm going to construct a confidence interval. So surveyed the class, and only 4 of the 60 students were from New York. So I'm setting S equals to 4. What the code does, let me just run it first and show you the plot, and then we'll go back and look at it. And this takes a few seconds to run. Okay, so this is a 0.99 confidence interval for P, given the data that we observed in class today, where 4 of the 60 students were from New York. So this purple value, this is plotted at 4 divided by 60. I should be able to do this in my head, but I'm putting it up here. So that's P hat equals 0.066667. And this is the confidence interval that surrounds that estimated value. So it runs from, well, we'll pull out the specific values in a minute. So in particular, it does not include, the confidence interval does not include 0.24. So we reject the hypothesis in our small sample of 60 students that the proportion of graduate students from New York is equal to 0.24. So that's an interesting finding. Not unexpected. Okay, so let me go back to the code and explain how this works. So again, like I said, to construct the confidence interval, you have to do a bunch of hypothesis tests for different specified values of P, and we collect the values of P for which we fail to reject the hypothesis. So these are the values of P that we're going to try. So I just picked some values that I thought would surround the confidence interval. So I'm going to try P equals 0.01 up to 0.5. Again, our significance level is 0.01. This vector reject is going to collect, we're going to fill it in with true falses, and we're going to put in a true whenever we, we're going to put in a 1 whenever we reject, and we're going to put in a 0 when we fail to reject. So that will help them further down in the code. Reject prob plays the same role that it played in the last chunk of code. So we're going to use this in how we construct the decision rule. So this is a harder calculation. You notice that it took longer to run because for each hypothesized parameter value for P, we have to go through the calculation that we did above to figure out what is the decision rule for that value of P that gives a significance level equal to 0.01. So it's going to be a double for loop. We're going to loop over the entries of pvec, the hypothesized values, and then we're going to loop over the entries of dvec, the possible decision rules. And then for each decision rule, we're going to figure out what the rejection probability is. Once we get all those rejection probabilities, we're going to figure out what the decision rule has to be. So we're going to get min d. And then once we have the decision rule specified by min d, we're going to figure out if we reject that value of P under that decision rule. So if the absolute value of our statistic S over N, which is P hat, minus the hypothesized value P vec of I, if that thing is bigger than min D, then we reject, and we're going to set reject of I equal to 1. If not, so else means if this is not true, so if the absolute value of S over N minus P vec is less than min D, then we're going to put a 0 because we failed to reject. Okay, so let's run that again. And let me show you the results here on the console first. So if I do cbind pvec reject, okay, so this is a 2-column matrix that I just printed out. Ooh, this is a big one. So the first column are the values of pvec that we tried, and the second column are the values of reject. So you notice that we rejected p equals 0.01. We rejected p equals 0.013, but we failed to reject p equals 0.014. So this value of p is going to be inside the confidence interval because we failed to reject. And we failed to reject all these values of p. So these are all in the confidence interval. And we failed to reject p equals 0.200, but we were able to reject p equals 0.201. So this one is not in the confidence interval. And then the next line of code just makes that plot. Most of these commands are familiar. One of the new command, okay, so there's a new command, points. So points is like the plot command. It adds plotting symbol, circles, to the plot. But if you do points, it doesn't create a new plot. It adds those points to the existing plot. So I'm just putting a dot at the p hat value. And HEI is where the height on the plot that I'm putting it in. You can add text. I added the significance level, the confidence level, 1 minus the significance level, to the plot. And then I added a p outside the plot. So if you want to add text outside of the axes, you use the mtext command. Okay, so that's it for the code for this section of the class.